How's it going, everyone? This video we're going to have a look at independence for independent events. So if we're tossing a coin, okay, so we've got just a standard coin, and if we toss that however many times, okay, toss one, okay, we have a 50% chance of either getting a heads or 50% chance of getting a tails. If we toss it again, okay, it's exactly the same as results for the first one, or probabilities. So I still have a 50% chance of getting heads. I have a 50% chance of getting tails. And if I do it again, I toss the coin a third time, I still have a 50% chance getting heads, 50% chance getting tails. And this essentially repeats. Now, contrary to some belief, um, each toss is independent of each other toss. And this idea is basically independence. What people get confused about, and it's called the gambler's fallacy. Um, where if I have, let's say, I get a heads on my first toss, a tails on my second, I get a head, a head, a head, a head. So that's 1, 2, 3, 4. Might get another one, so that's 5. So I've got 5 heads in a row. And the gambler's fallacy suggests, or logic, I guess, we start to look at patterns and say, well, we've had 5 heads in a row. It's probably time we had a tails. Okay, so we're looking at past events and saying, well, there's 5 heads in a row. Well, chances are we're probably going to get a tail to even out. This is incorrect because each coin is independent of each other toss. It is 50% every single time. Slightly different to tossing 1, 2, 3, 4, 5, 6, 7, 8. So if I was to toss 8 coins at the same time, okay, chances of getting heads and tails, I'll expect to get 4 heads and 4 tails. Okay, however, I might actually get 1, 2, 3, 4, 5, 6 heads and 2 tails. Well, the chances of getting that is slightly lower than getting 4 heads and 4 tails, which is what we expect. Um, yeah, so slight difference. If we're tossing it in consecutive order, so 1, 2, 3, our chances are exactly the same every single time. So don't worry so much about this stuff here. It is called the gambler's fallacy. I've put a link to a video which explains that a bit further. So it is interesting. So independence, every event is independent of each other. Now we had a look in the last section for probability of A given B, and we found that it's the probability of A and B divided by the probability of B. And then we rearranged that, so we found the probability of A and B is the same as the probability of B times the probability of A given B. Now, if we have an independent event, the probability of A given B is just going to be the probability of B, because I can't, like I said in the last video, if they're two independent events, here's A, here's B, I can't get, if I select B, I cannot select A because there's no intersection. Okay, so they're completely independent of each other because there's no crossover. And so what we find is if I chose B on my first go, the probability of choosing A given B, well, I can't get A, so it's just the probability of B. So for independent events, I can say the probability of A, well, that should be an A, by the way. the probability of A given B is just the probability of A times the probability of B. So this is for independent events. Okay, so it's that formula there. So A and B is the probability of A times the probability of B. And this result is used to test whether events are mathematically independent or not. So if they're independent, we'll find that the probability of A and B is the same as the probability of A times the probability of B. So just keep that in mind. So looking at example 8, we're tossing a coin twice. And we've got 3 events. A is the event that at least one of those is a tail. So one of the tosses is a tail. This event B is either 2 heads or 2 tails. And event C is the first toss is a head. And to start off with, we want to list the sample space. So A, at least one tail. So we can either get a head and a tail, or a tail and then a head, or we could get 2 tails. Okay, so there's really only 3 there. They're the only ways I can get event A. Event B, either 2 heads or 2 tails. Well, there's only 2 ways, heads, heads, or tails, tails. In event C, the first toss is a head. So if the first toss is a head, I can either get 2 heads or head and then a tail. So there's only 2 options there. Just testing for independence, we're going to test if A and B are independent. So remember our formula, probability of A and B is the probability of A times the probability of B. So if that holds, then the A and B are independent. Now the probability of A, okay, there's 3 different options there that we found. And there's only one missing. So I should have drawn out. So you can either get heads, 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 tails, tails, heads, or tail, tail. So there are only 4 options in total that we can get. So it'll be 3 out of 4. And the probability of B is going to be 2 out of 4. So A and B, what occurs in both A and B? Well, we've got 2 tails. So probability of A and B, well, there's only 1 out of the 4. So to put the values and to test for independence, we've got our left-hand side. So left-hand side is only, well, it's 1/4. Left-hand side, probability A and B is 1/4. So 1/4. And then the right-hand side, so RHS, probability of A, which we found was 3/4, times the probability of B, which was 2/4. If we work that out, we get 6 out of 16. Which is just 3 out of 8. Now, because we've got 3/8 and 1/4, we can say the left-hand side does not equal the right-hand side. So therefore, A and B are not independent of each other. So now we're just going to have a look at whether, to test whether B and C are also independent or are independent. So again, we need to find probability of B, as before, was just 2/4. And the probability of C is going to be pretty much the same, so 2/4. And we can have a look at the probability A and C, sorry, B and C. Well, B and C, there's only heads, so there's 1/4. And like before, our left-hand side is the probability of B and C, which is just 1/4. And then the right-hand side is the probability of B times the probability of C. So 2/4 times 2/4. So we get 4/16, which is 1/4. Now, because this number and this number are the same, we can say the left-hand side is equal to the right-hand side. So therefore, B and C are independent events. And the last little question is, use the addition formula to calculate the probability of B union C, in other words, B or C. So if you remember our addition formula, the probability of B union C is equal to the probability of B plus the probability of C minus the probability of B and C. So because we found out that B and C are independent, we can say the probability of B and C is just going to be the probability of B times the probability of C. So rearranging, we get probability of B or C is equal to the probability of B plus the probability of C minus the probability of B times probability of C. And we found the probability of B was 2/4, or in other words, a half, plus probability of C, which was also 2/4, or another half, minus, and it'll be a half times a half. So half plus a half, we get 1 minus a quarter, so we get 3/4. So that's the probability of B or C. So for our last example, we've got three athletes commencing a fitness program. So they're training for a competition of some sort. So we've got Ari, Barry, and Chris. Now the probability is that they stick to the program. Ari is 0.6, Barry is 0.8, and Chris is 0.7. And we want to work out the probability that all three stick to the program. So we'll say the event A, so let's define event A is that Ari sticks to the program. B is going to be the event that Barry sticks to the program. And C is obviously that Chris sticks to the program. So therefore we can say the probability of A is 0.6, the probability of B is 0.8, and the probability of C is 0.7. And we want to work out the probability that A and B and C all stick to the program. Now, since they're all independent of each other, we can say that the probability A, N, B, and C is just the probability of A times the probability of B times the probability of C. So 0.6 times 0.8 times 0.7. If we work that out, we'll get about 0.336. So we can say the probability that all three stick to the program is 0.336. Second part of the question, we want to find out if only Chris sticks to the program, and what's the probability of that. So if only Chris sticks to the program. So we're going to look for the probability that A, Ari does not stick to the program, the probability that Barry doesn't stick to the program, but C does. Now, probability of A dash, N, B dash, and C is going to be the probability of A dash times the probability of B dash times the probability of C. Now, we don't have these two numbers, but we can find them, and that's by using our complementary formula. So 1 minus the probability that they do stick to it times 1 minus 0.8, and then times C, who does stick to it, 0.7. So we'll actually get 0.4 times 0.2 times 0.7, which is 0.056. So there's a 0.056 chance that only Chris sticks to the program. And the final one, we just need to work out the probability at least one of the three stick to the program. At least one sticks to the program. So the events that at least one of the three is the complement of the event that no one sticks to the program. So okay, so the probability at least one person, or at least one, is the complement of the event that no one sticks to it. So the complement of no one sticks to the program is 1 minus the probability of A dash, B dash, C dash. So it's going to be 1 minus the probability, the probability of A dash times the probability of B dash times probability of C dash, 1 minus, and we found out before that's 0.4, 0.2, and this one is going to be 1 minus 0.7, which is 0.3. So if we work that out, we get 0.976. So we can say the probability that at least one person sticks to the program is 0.976. So that wraps up for the chapter on independence. So have a go at the questions. Thanks for watching.